We looked at having an extra tape. We looked at having a two-dimensional address scheme, adding a second dimension to the tape, which is kind of like having extra tapes rather than a finite number of tapes. It's an infinite number of tapes. And we determined that for any of those, they weren't actually more powerful than just a simple Turing machine. And we ended talking about this. If you're designing things with the smallest branching factor, you want to use a simple Turing machine because then the actual action selection is minimized. And on the other hand, if the goal is to create a Turing machine program, maybe you want to use one of these more complicated schemes because you can represent more complicated knowledge in less work or fewer transitions. So where we're headed from here before we move into the theory of computability is we're going to talk about some non-deterministic Turing machines. So we've basically been talking about deterministic Turing machines this entire time, right? Given that you have a particular input symbol, we haven't really allowed for non-determinism. None of the changes that we've made to the Turing machines so far have affected their computation power at all, but we also haven't talked about non-determinism at all. So intuitively, what do we think here? If we allowed for non-determinism in Turing machines, how would that affect their power? What this means is for a particular symbol that we see on the tape and a particular state that we're in, we may have multiple options for what we write on the tape and for the direction that we move. Any thoughts?
I mean, it feels like it's more powerful, at first thought, like, just because like you have more, I don't want to say choices, but there's more things you can do, which doesn't feel like it's like just adding another tape, but it feels like it's a whole other aspect of, like, usually when we've done like, forget what it's called, but basically when you can make transitions with like lambdas, it
Yeah.
feels like there's a little bit more power to what you can do. And I would feel the same thing is true for Turing machines that are non-deterministic.
It didn't add any power in regular languages to add that, but it did add power in context-free languages to do that. So to think about whether it's more powerful, think about whether there is a language that could not be represented in a deterministic form that could be represented in a non-deterministic form. Whenever we add non-determinism, the efficiency skyrockets. So obviously, for any language, you add non-determinism, the ability to reach your conclusion faster increases. But it's also not necessarily mechanical. And by that, I mean, it's not something that we can simulate with a computer. Computers aren't non-deterministic. Computers are deterministic. So to add power, we have to be able to recognize additional languages. And I'm not necessarily saying the answer is no. I'm just trying to clarify what non-determinism is here so that we make sure that is there some class of languages that we could accept with non-deterministic Turing machines that we couldn't have with deterministic Turing machines? So because we can't really simulate this with a computer or think about it as a computer because it's not mechanical, we need something else. We need some way of defining a non-deterministic Turing machine. So anything that rejects or enters an infinite loop is irrelevant in non-determinism. If those happen, we just ignore them. We just stop considering them. If any particular thread leads to acceptance, then we accept. How do we make the argument? We're going to attempt to simulate a non-deterministic Turing machine with a deterministic Turing machine. If we are able to do this, then we can consider them to be in the same class. Does that make sense? It would be like saying is your computer at home equivalent to a PlayStation 2? Using the same argument from yesterday. If your computer is capable of simulating a PlayStation 2, then it's equivalent to a PlayStation 2 in some sense. So the deterministic Turing machine needs to keep track of all of the configurations of the non-deterministic Turing machine and update them based on what happens as the non-deterministic Turing machine works. As usual, I'm not going to go into the full proof. I kind of want to give you the intuitive idea of how we would go about doing this. The actual process is less relevant or important, but the outcome is very important. So we need to simulate all configurations of all threads of the non-deterministic Turing machine on the deterministic Turing machine. If you go down that rabbit hole, you will find there is an equivalent deterministic Turing machine for every non-deterministic Turing machine, which means that we can construct a Turing machine to simulate a non-deterministic Turing machine for any non-deterministic Turing machine. And this also makes sense, right? This is just saying, can you design an algorithm to solve a non-deterministic problem? So for instance, if I said, my password is less than 20 characters long, non-deterministically, I tell you what my password is and you verify it. Deterministically, you would have to go through all possible configurations, but there is such an algorithm that exists. Eventually, you would be able to tell yes or no, my password is less than 19 characters or not. It just might take a very long time to do so. But the idea is if you can come up with and construct a non-deterministic algorithm, there exists a deterministic algorithm that will simulate that non-deterministic question or non-deterministic algorithm. So that's a very important result. It just so happens that as computer scientists, we also care about efficiency. There is still one difference between any Turing machine, including all of the prior options we've discussed so far, and a computer that you are actually using. And the big difference is that the modern computer is reprogrammable. The Turing machine that we've talked about basically halts on a tape, but then you need to swap out the tape with a new program or reposition it to a new program to be able to run it. So what can we do with a Turing machine to make it reprogrammable? And the basic way we're going to do this is we're going to design a Turing machine. And this Turing machine is going to take as input basically a written out description of another Turing machine. I guess that's the best way to describe that. And an associated input string. So you can imagine finding some way of describing the actual Turing machine. What are the possible states? What are the possible transitions? You encode all of that into some string, some parsable string, and then you also give it some input. And if we had that parsable string, then it would be possible to write a program that would parse that Turing machine and that string to determine whether that Turing machine accepts that string. Does that make sense? It would be like saying, you're going to write for your project the CYK algorithm. You're going to write a program that is the CYK algorithm. I'm going to write a program that takes as input your program and a particular grammar. And my program will spit out yes or no. Your program correctly determines the output of the CYK algorithm on that grammar. Does that make sense? these kinds of generic arguments are gonna start getting more and more abstract and theoretical, so finding some way to ground yourself as we do things, really strange things like feed Turing machines, other Turing machines. And strings. I can get really abstract and theoretical, so I want to make sure that we are all on the same page there, yeah.
It's like when you make a method and you call that method another method.
I suppose, yeah, it kind of simulates, I would think of it like, more like a test, more like a very comprehensive unit test that simulates the entire program on a particular input. That's what a unit test does, right? It gives you a particular input, and then it determines whether or not your program handles that input in the way that you expect. So it's very much like a verification or a test, or you can also think of it like writing autograder software. If you wanted to write a program that was able to take as input an entire class's set of algorithms and determine whether or not those algorithms are correct, that's where we're going. So a universal Turing machine would be able to take as input the description of another Turing machine and a string and simulate the computation of that Turing machine on that string and determine whether or not it works or not. Right? This is what we can do with a computer. You can launch an application, do something with it, close that application, launch another application, do something with that, and the computer can handle all of that. It's reprogrammable. So we call this concept a universal Turing machine. It's a Turing machine that's capable of reading other Turing machines and simulate other Turing machines on particular input. The actual process of this also becomes less important. There are ways that we can represent Turing machines like this. For now, it's more of a theoretical argument. We don't really need the practicality of actually being able to do this ourselves. We just need to be able to reason about whether or not it is possible to do something like this. So any Turing machine has an encoding of finite length, meaning that it's not ever going to be an infinite encoding. It's just there's going to be a length of characters, zeros and ones, that describe this Turing machine. We can encode a Turing machine as a binary string. And that uniquely identifies that Turing machine. Just like in binary, we can uniquely assign a machine instruction to that binary. You make the binary longer and longer, there become more and more and more options. And so with a finite length, we can encode any particular Turing machine in a string that represents that Turing machine. Given a particular encoding of a Turing machine, we want to be able to do the reverse. We need to be able to decode it and figure out what it does. So given a Turing machine, we can create a string. Given a string, we can reconstruct the rules of the Turing machine. So it is possible to do this. Again, I'm not going into the details of exactly how, but the important result is that we can do this. We know that a Turing machine can emulate another Turing machine because of this. Because we can do this, a Turing machine and a computer are equivalent. As long as we have such a way to encode our Turing machines and decode our Turing machines, now we have exactly what a modern computer can do. Questions on any of these concepts? Very theoretical, but very important to what we're about to talk about, or what we're going to go into some detail about, which are the kinds of languages that we can't represent with any of the rules that we've talked about so far in class. Before we do this, we need a little bit of background. I am not 100% sure this was covered in discrete, So I figured I would at least make some content about it to hopefully refresh people who have seen it before, and if you haven't seen it before, then this becomes a good way to introduce it to you. So we're going to talk about countable and uncountable sets. We'll start with a basic question. What is a set that is countable?
They're all real numbers?
Set of all real numbers is countable?
Does it mean any like infinite set?
So every non-infinite set by definition is countable because you can just enumerate all of the options in the non-infinite set. This gets interesting when we start considering infinite sets. So good, anything that is not infinite, anything that a finite set is countable by definition. You start with the first element and go to the last element. But what if there is no last element? Are there still countable sets that are infinite?
In normal definition or like. Cause instead of integers is countable. You can count. You can like assign. It's literally just like. You can assign 1 to 1, 2 to 2, 3 to 3, 4 to 4.
Yeah,
Like the set of even integers, you can assign 2 to 1, and then you can assign 4 to 2.
two, and yeah,
And you
So-
come up with an equation that generates. One of the numbers in the set given an input one.
yeah. And the only thing that's left that you need to show is that for any element of the set, there exists an index that maps with that expression to get you that element of the set. So the expression for the even integers would be something like the index times 2. So if I ask what is the 8th even number, you can tell me that. What is the 24th even number? You can tell me that. So you have a mapping from the set of positive integers to the infinite set. If you have that mapping, then it is countable. So we'll start with the set of positive integers because that is the basis that we're going to use for exactly this argument. Is the set of positive integers countable? Yes. You start with 1 and then you just continue to add 1 to generate the next one. It is an infinite set, but if you give me any positive number, I can tell you how long it will take me to get to your number. You cannot tell me a number that I will not get to. If I started counting right now and didn't stop until I died and then passed it on to any children and said, all right, your entire purpose in life is to keep counting after I die. Also, you need to reproduce so you can do the same thing to them and just continue this process forever. Eventually, they would get to whatever number you tell me, regardless of how large it is, given an infinite amount of time. So the set of positive even integers is countable because you can map the set of positive integers onto the set of positive even integers. 1 goes to 2, 2 goes to 4, 3 goes to 6, 4 goes to 8. How about the set of all integers, including negative integers? Is that countable? How do we map the set of all integers onto the set of positive integers?
Because if you try to map, and this is, I can't really do anything at the moment, but if you try to map 1 to 1 or 1 to -1. You couldn't do because you have like 2.
Yeah, we kind of have 2 directions to go, right? We have the positive direction and we have the negative direction.
It's right.
So we can kind of start going in one direction or we can go start going in the second direction. Is there anything more intelligent we can do that would make this possible?
I mean, so obviously we need 0 as well, but.
Yep,
On top of 0, I mean, it'd be kind of like the same thing, well, not the same thing, but. You're basically having double the thing that you were able to count, if you think about it that way, like. You have set from like 1 to whatever infinity, and then if you took off the negatives off of. Those same like items, which are the countable, those numbers. It would be just like you're counting double of what you.
so what I'm going to recommend that we do, we're gonna start with 0. We're gonna go to 1, -1, 2, -2, 3, -3. Kind of like this. So if we write them out as 0, 1, -1, 2, -2, 3, -3, 4, -4, 5, -5, etc. Is there a mathematical function that generates this? What would that be? We want to map this to 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and 11.
Something with like an exponent and -1 and.
You can add and then subtract. Like add 1, subtract 2, add 3, subtract 4. I
Yeah,
don't know if that really works, but
so we've defined a sequence.
Yeah.
How do we turn that into an expression? So the first thing to recognize is ignoring the positive negative flip. How could we do it? I think it's easier if we don't worry about negatives. How can we generate 0, 1, 1, 2, 2, 3, 3, 4, 4, 5, 5?
Like the. Index divided by 2.
Yeah, it's the floor of it divided by 2. But, or the integer division of it into. Yep. So 1 divided by 2 is 1/2, the floor is 0. 2 divided by 1 is 1. 3 divided by 2 floored is 1. So now we just need to find a way to alternate negative, positive, negative, positive, negative, positive, taking the floor of it divided by 2.
Yeah, you just have that -1 plus an exponent, and then, so it just keeps flipping on.
Yep. Yeah, you take -1 to this power. All right, so this power -1. So that's the answer. We have something like -1 to the n times the floor of n/2. That'll get you there. So you can do that with any countable set if there exists a way to do this. And so this becomes a very interesting way to count an infinite set that can go off in multiple directions, or you have multiple dimensionalities, even though they're kind of parallel single dimensions. You have the positives going on forever, you have the negatives going on forever, and you have 0. This becomes a very elegant way of aligning everything such that it is countable. Have people seen this before in discrete? Sorry, my back was turned. Have people seen that in discrete?
I've seen other stuff, but not.
Interesting. I always try to bring this up in discrete because it's really interesting. How about the set of all rational numbers? I think we talked about this earlier this quarter. Did we talk about how to generate all the rational numbers? Do people remember whether or not that's countable and how you do it? So rational numbers are any number you can get as the quotient of 2 integers. So you take an integer divided by some other integer and you get a rational number. So 1/9, even though it's an infinite repeating 1, 1, 1, 1, 1, 1, 1, is rational. Because it can be represented as 1/9. So is the set of rational numbers countable, and if so, how do we do it?
I feel like maybe not.
I believe it is. I remember in like the squiggly on, sort of like what he did last time. You go from if you have like a
yeah.
box. and you go
Yep.
like This.
Yeah. Yeah, so we had the numerator on one axis and we had the denominator on one axis. And we're kind of gonna take a squiggled path through it where we take the first diagonal, the second diagonal, the third diagonal, the fourth diagonal, the fifth diagonal. And you will repeat some numbers. You will see that you get 2/1, 4/2, 8/4. So you're gonna generate 2 a bunch of times. You're gonna generate 1/2 a bunch of times. But you can continue this process and know, given any particular rational number, how long it will take for this process to be able to generate. So the set of rational numbers is also countable. Which is really interesting, that we could continue to produce them. Yes, there are an infinite number of them, but given any particular rational number, that algorithm will eventually produce it. It may take longer than the Earth has left, but it will happen. Given an infinite amount of time. So what's a set that's not countable?
All the numbers between 1 and 2.
All the real numbers between 1 and 2?
Just all possible decimal values between 1 and 2.
What are the real numbers between 1 and 2? Real,
yeah.
that's basically, yeah. Real is the set of rational numbers plus all numbers that can not be represented as a quotient of 2 integers. So any number that exists, pi is a real number, but as far as we know, pi is not rational. It's infinite, there's no repetition in there at all. So how do we get the concept that the set of real numbers is not countable? We'll go between 0 and 1 to make it easier, because this is basically what the, double dot generate a random double does. Double dot random double, whatever we use to generate random doubles, it gives you a long random string of digits. How would you go about it?
You can always add something to the end of the decimal, like you can add any number you want at any time, you can always generate a new number. You're never at a point where you can just like count to the next one without being able to like add more to it.
So that's not quite a proof though, because we could say the same thing about the set of all integers. Basically, you assign a way of iterating it and say, all right, we're gonna start at 0 and go 0, 1, 2, 3, 4, 5, 6, 7. There's no way we'll generate -1, therefore it's not countable.
I've seen a proof for this.
There is a proof for it, and I will show you the proof for it. But it's not quite as simple and straightforward as you would like. Because you can iterate and say, what are all of the real numbers that have decimal length 1? 0.1, 0.2, 0.3, 0.4, 0.5, up to 0.9. And then you could look at all of them that have length 2, 0.10, 0.11, 0.12, 0.13. But we'll never generate something like pi that way, because it's infinitely long and doesn't repeat. So that process would never generate an infinitely long number. In fact, it wouldn't even generate some rational numbers like 1/9.
I think the proof goes something along the lines of assume you have like the set of all the numbers between 0 and 1. And you can just like take something from that and add something to it and have something that's still between 0 and 1, but wasn't in that list of numbers you had.
So we're gonna just start assuming, with no ordering whatsoever, that we have our list of real numbers. We're gonna assume, for a proof by contradiction, that all of the real numbers between 0 and 1 are in this list, regardless of how long they are. So we're going to write out so this list may be infinitely long, but here is a list of them. Each of these numbers may be infinitely long, but that's okay. What we're going to do is, we've now done this, right? We're going to make the assumption that this list is complete. In order to prove that this list is not complete, even though we say that it's complete, we're going to start generating a new number down here that is a number that is not in this list. How do we do it? We take this first digit and we add 1 to it. And if we try to add 1 to a 9, we'll wrap around, mod it by 10 and get 0. So in this way, this number is distinct from this number. let's say that this first digit is a 7 and the second digit is a 9. We're now going to look at the second digit of this number. And we're going to mod it by, add 1, mod it by 10, we get a 0. This number is now distinct from this number. We'll move on to the third digit. The third digit here is a 6. That tells us that this is going to be a 7. This number is now distinct from this number. You continue this process infinitely, because this number may be infinitely long. This process won't necessarily terminate, but you can reason at least that if you continue to this process over this infinite list of numbers, you would be generating a new real number that is distinct from every number on this list. We call this a diagonalization proof. In fact, there are many different kinds of questions we can answer with a diagonalization proof. Does that make sense? Questions on how this shows that this is not a countable set? No matter how you do this, you can always produce a new number that's not in the list with diagonalization. You just make it distinct from every number in this list at the associated position. And suddenly you have a new number. So it turns out that there are some sets that are not countable. So they're infinite and we can't even generate them. We can't have a process that will generate them. So an important question we might care to ask is why? Why do we care to distinguish between sets that are countable and sets that aren't countable? It's important because of being able to write algorithms for them, right? We need some way of being able to produce an enumeration procedure for a lot of different kinds of sets, to be able to continue to produce new values and new values and new values and new values, and eventually keep generating new ones. Note that we say that it's an algorithm and not a procedure, because this may not terminate. This entire process may not terminate. But we call it that because what it says here is it produces well-defined and predictable results. I can't think of a better way to state that, but well-defined means that it has a particular order to its output. It's predictable in that you know what it's going to generate. It has the same form as it continues to generate the new things. Like pi is not a predictable result. You can't look at the first 10 digits of pi and be able to predict what the 11th is going to be based on the first 10 digits of pi. It's not predictable. But if you have a particular expression for being able to generate the next rational number or the next integer in a set, then what you have is something that is well-defined because there's an expression for it and predictable, given that you have You've done this many of them, the process for generating the next one is clear. What all of this means is it can all be simulated on a Turing machine. If a set is countable, then a Turing machine can do this. It can start generating these. If it's not countable, then it's beyond the power of a Turing machine, which also means that it's beyond the power of anything that you could program in a programming language. No algorithm exists or can exist that prints all of the real numbers between 0 and 1. You would be able to come up with, regardless of how you come up with that procedure, there will be some number that your algorithm will not generate. We'll look at an example real quick before the end of class. So going back to kind of our terminology and way of thinking for the class, we'll have an input alphabet ABC, and the set is going to be anything from this alphabet that's at least one or more of these symbols. So we have that plus that is the positive closure, means that sets of one or more elements. So the empty set is not possible here. So the list might be something like A, B, C, AA, AB, Is it countable?
I think so.
Seems like it.
Disagree.
We have some way of generating everything of length 1, some way of generating everything of length 2, everything of length 3. There are an infinite number of these possible strings in this set, but there's at least an enumeration procedure that is well defined and also predictable. Given any one, if you had that algorithm for generating them, you could yourself figure out what the next one that's going to be generated would be. Now think about listing them all in alphabetical order. Is listing them in alphabetical order an enumeration procedure? What would that list look like?
An infinite amount of strings that are only A's followed by.
A.
You'd eventually reach a lot of A's and then a B.
I don't think you would.
Well, you wouldn't because you'd have to write an infinite number of.
Yeah,
A's.
you would never terminate that procedure generating more and more and more and more A's. You would never generate B or AB or C. So it's not an enumeration procedure because given the definition of the procedure, you can come up with a string that would not be generated by that procedure in a finite amount of time. So even though this is a countable set, there are ways, there are procedures that show that it's countable and procedures that show that it's not countable. So you have to be careful if you're making an assumption like assume that you're counting in this particular way because that doesn't actually prove anything. If you list all the strings in length order, on the other hand, this is an enumeration procedure because any string that you give me has a length, which means that I can tell you how long it would take until this procedure generates that process or that string. So what this means, we can count Turing machines, right? We said there are a finite number of Turing machines that we can basically list as binary strings. And since binary strings are countable, Turing machines are also countable. You could just generate all possible binary strings. And eventually you would have a legal definition of a Turing machine, which you could add to the list of possible Turing machines. This is an infinite process. There are an infinite number of Turing machines, but now we have a way of enumerating and producing Turing machines. Which seems ridiculous, but it's a really important result. So we'll come back tomorrow and talk more very high level theory. But sleep on this and think about the power of computation. Let's see you tomorrow.
Once.